Okay, so let us start physics, and the first chapter of course is units and measurement. Why is this almost always the first chapter in nearly every physics book? We are going to come to that, okay, but let us first see what units are. So whenever you measure a physical quantity, it always involves comparison with some known standard which people have agreed upon, and these known standards are called units. And whenever you make a measurement of a physical quantity, the result always has two parts. The first part is a number, and the second part is that standard unit. For example, you want to weigh a stone and say you use balance or some other device. The result of that measurement may look like this: 1.58 kg, kilogram. So this kilogram is the unit part and this is the numerical part. There is a definite meaning of this kilogram. There is a precise meaning of what 1 kilogram is. So that people already agree on, and this 1.58 tells you that your stone or whatever you are weighing has 1.58 times the weight of that 1 kilogram. Okay, so this is how the result of a measurement looks. Now, there are many physical quantities. There is a large number of physical quantities. So, do you need a unit for each one of them? Yes, you need. But the job is made easy by identifying some base or fundamental physical quantities. And the units that come with these quantities are called fundamental or base units. In what sense are these quantities fundamental? See, in the sense that the other physical quantities, each one of them can be expressed as some kind of combination of these base quantities or the fundamental quantities, and those other quantities are called derived quantities. Because they can be derived from the fundamental quantities as their combinations. And the units that the derived quantities get from similar combinations of the fundamental units are called derived units. Now, a complete set of units, both fundamental as well as derived, is called a system of units. So, there are quite a few of them. See, initially what happened is that in different countries, the people who used these units, they used different systems of units. This created a non-uniformity and there was a lot of confusion. So at some point, people decided that no, we want a single system of units throughout the world. Initially, these were some systems. CGS system. These letters C, G and S come from the units for these fundamental quantities. C denotes centimeter, G denotes gram and S denotes second. So these are some units for the fundamental quantities or base quantities of length, mass and time. Okay, so that is why that system is called the CGS system. This was in use. Then you also have the FPS or British system. where the unit of length is foot, unit of mass is pound, and unit of time is second. This is still used in, for example, the US, North America. You also have the MKS system. In which the units of length is, the unit of length is meter, the unit of mass is kilogram, and the unit of time is second. So you can see that second seems to be a very convenient unit, that it is appearing in every system. So that one system of units which later people adopted throughout the world is the SI system. These initials come from the French Système International d'Unité, or in English, the International System of Units. Okay, it was developed in 1971 by the International Bureau of Weights and Measures. So in this system, actually this is an extension of the MKS system. In MKS system, all the fundamental units were not included that we have nowadays in SI system. So this system was extended and we have got the SI system. So let us see what the fundamental or base quantities are and what their units are in SI system. So since it's an extension of the MKS system, so these units you are going to see. So first of all, and one more thing, if you want to really see, you can visit their website. You can visit this website, the website of the International Bureau of Weights and Measures. There you will actually get the meaning of every base unit and all the things are given there. Okay, so you go there and on that website, you see there you will find some places where you can click. So there one place is there, technical / scientific. Okay, so you click on that, a drop down menu will come. There you will see this SI, I think. The first item itself is SI, the SI in fact. You click on that and there you will get all the base units. But anyway, the base units are this. The base unit for time is, it starts, for some reason it's given like this, it starts with time, is, the unit is second. There is a precise meaning of what 1 second is, how much time 1 second is, which is available there. Or you can see the book also, in the book also it's given. It is defined in terms of frequency of cesium-133 atom, something like that is given. Okay, we need not worry too much about that right now itself. And the symbol that we use is S for this unit, time. Then we have length. The SI unit of length is meter. And the symbol we use for that is M. And then we have mass. The SI unit for mass is kilogram. And the symbol is kg, not capital Kg, okay. lowercase k, lowercase g, small k, small g. Like that, small s and small m, not capital M. Then you have electric current. The SI unit for that is ampere and the symbol is capital A. We will of course gradually know what these units are, what their definitions are, but right now this is just a list of what the fundamental units are. There are 7 of them, plus 2 additional units are also there for measuring angles. I am coming to that later. So after electric charge you have thermodynamic temperature, and the SI unit for this is Kelvin. You do understand or already know that these units have been named after physicists, ampere, Kelvin, and the symbol here is capital K. This is for thermodynamic temperature. Then you also have amount of substance. Here the SI unit is mole, M-O-L-E, and the symbol is M-O-L. And you also have another one, because 1, 2, 3, 4, 5, 6, another one, this is luminous intensity. And the SI unit is candela and the symbol is CD. So these are the 7 fundamental or base quantities, physical quantities, and the SI units of them along with their symbols. All the other quantities can be derived from these quantities as some kind of combinations. Okay. When we get the other quantities, for example, you can consider the physical quantity speed. You know what speed is. Speed is the amount of distance covered by a moving object. If I am talking about average speed, right now we are not really going into average, instantaneous speed, those things. Speed is the average speed. Okay. Actually, you can consider instantaneous speed also, but for the sake of simplicity, let us consider average speed. An object is moving slow or fast, we don't really, during its journey, whether it slows down or it speeds up, we are not taking those things into consideration, say, for the moment. To go from point A to point B, which has a definite distance between them, an object took time, say t, and say that distance is s. Then the average speed is s divided by t. So from this relation itself, you see that the physical quantity speed is a combination of length and time. Okay. Perhaps I should use d here. So if you are thinking of the SI unit of speed, it will be meter divided by second or meter per second, because that's what speed is mathematically. And as such, the SI unit will be like this. It can be written like this or like this, meter per second. So this is a derived quantity. There are other derived quantities also, and the units they get in SI come from the units of this physical or base, fundamental or base quantities. Now the other two additional units for measuring angles are radian for measuring plane angle and steradian for measuring solid angle, about which we will talk more later. Okay, plane angle you perhaps already know from trigonometry itself. You have got the idea of what 1 radian means. In fact, why also we use radian and not degree when we study calculus. So radian is an important measure for measuring angles. There is a notion of a solid angle as well. A solid angle, you can think of a solid angle as the angle that you get when you think of a cone, say a right circular cone. That angle at the vertex of the cone, that thing is solid angle, and that angle has the SI unit steradian, whose definition is somewhat like radian. Okay. Now comes the most important question. Why do we measure, and why do we need to measure physical quantities? See, you have to understand that whatever we do in science, everything depends on experimental verification. See, what happens is this. Say you are studying something. Okay, and that's something, so this is something. With that something, there are associated some physical quantities which may be of interest to you, which are some variables, say V1, V2, V3. So you are interested in these three variables. These are not velocities, okay. These are just some physical quantities associated with that experiment, that's something. And you want to know how they are related. So what do? You set up an experiment, like what you do in physics laboratories. You set up an experiment which you believe will help you study that phenomenon which you are studying, about that something which involves these variables. Then what you do? You conduct the experiment and make measurements. So you get some values for V1, V2 and V3. Say you get these values, A1, A2, A3. You do the experiment once, you get these values, and in a slightly different times there, I would say, the experiment goes on, right, for some time. After some time, the values change, B1, B2, B3, and then after some more time, you again make measurements of these variables and you get other values. So like that you get many values. And then looking at these values, you start wondering, how can these quantities possibly be related to one another? Okay, you start thinking about that. And after much thought, you come up with an idea. You plot these quantities on these values on graph paper, you see the graphs, you do many things, you just do, you just think about this entire thing intensely, and you uncover some kind of law, say, some kind of relation. I'm just simply giving an arbitrary relation, okay. You uncovered something like this from the data, okay, and maybe you get some other relations as well. You then put forward a theory which helps you explain this data and these relations or equations, inequality, whatever you may come up with, they are parts of the theory. Now, the important question is this theory correct? So, you have put forward a theory and you announce that you have a theory for this new experiment. This is why these values are coming. So, what will the other scientists do? Will they just simply accept your theory? No. See, the thing is that you have to understand in what sense a theory is correct. To be more specific, let us just think of this equation. Which all of you are familiar with this. This is Newton's second law. When a force F is being applied on an object, on a body of mass m, and the mass is not changing, then the body gets acceleration a. And these three quantities, are related by this equation. So, this relation or this equation is something like that one. So, we call it Newton's second law, right? A special case of Newton's second law. And right now itself, I am not going into the details of this and the subtleties. Law means what? Does it mean that this law is always true? Is it an absolute truth that no matter what happens, this will continue to be true in any case? And the answer is no, it's not. This is what you have to understand about science. In science, everything is only temporary and approximate. You see, whenever you are conducting your experiment about that something, many things from outside were influencing that. Nature is so complex that it is nearly impossible to take into, nearly means actually impossible to take into account everything that may be influencing your experiment. And even if you take into account a large number of those influencing factors, the equations or these things that ultimately you will come up with, they will include those things, so they will be so complicated that they will be useless. You won't be able to solve them to say anything about this thing, this something. So what the scientists do, they neglect many things, and by doing so, they dilute the thing, because that's the best we can do. We cannot work with extreme complexity, that's impractical also. So, and then what happens? The theory that you erect from that simplified situation is not representing the actual reality of that something, but it is only telling you something about that something approximately. But very often means almost always, these approximations are so useful that everything you see around us, every kind of scientific invention is the result of some such theory which actually only approximates the ultimate reality. So every theory is only some kind of approximation. The exactness and precision of mathematics stays within mathematics itself. The moment you start applying mathematics to outside world, you see how complex things are, and you have to rely on approximations only. Okay, now what happens is that, okay, so you understand that Newton's second law is also actually only an approximation, right? So are there situations where this law breaks down? Yes, there are situations. So that's the nature of the correctness of anything, any law or anything in science. It's always subject to revision. If you are you will use some kind of device for measuring these variables, right? Now the device that you are using has its own limits. It can measure only that much. But after say a decade or 40 or 50 years, that device will be more advanced due to technological development. So then if you conduct this experiment, your values will be more accurate, more finer values. That means the values will change. You will then have to go back to your theory and see that whatever you explained there, is that still true for these new finer values? If it's still true, then the theory survives and people gain more confidence in the theory. But again, that is always subject to revision. If at all some experiment is performed which comes up with some new values that do not match with the theory's prediction, why prediction? You see, you can only measure the values of this variable at some times. So the theory tells you what the other values should be at the times where you did not measure. The theory tries to give you the full picture by only using bits and parts that you have actually collected from the physical experiment. Okay. So if at all you get a new value which starts to cause problem, say you get a new problematic value which does not match with your theory, what do? Where did the correctness of the theory go? It just went out of the window. Because it was approximate, any theory is always approximate. I mean, I am talking about scientific theories. This can happen, and this has happened many times. You can take the example of Newton's laws. Newton's laws continue to perform so well for a long time that people thought that they were absolute, that in no circumstance can they fail. But then when Newton's laws were applied to say objects moving with extreme speed, the laws really started to give nonsensical results. And that is why Einstein had to come up with special theory of relativity. See, there are situations where a theory will be taken to its limit, and if you go beyond that, then the theory will fail. So what do you then do with that theory? Do you just throw it out? No, that rarely happens, because the theory within its own range of applicability is still performing well. Usually what happens is that instead of abandoning the theory completely, you erect a larger theory so that the previous theory is only a part of that. That's how science progresses. Okay. In fact, these fundamental units, I have it here. The fundamental units of kilogram, ampere, Kelvin and mole. Initially, the definitions that were used for these things by the international standards of weights and measures, they went through a revision in 2018, and now the definitions are somewhat different but more accurate. So that's how science is not a static thing, it keeps on changing. And whenever you erect a theory, the sole test of validity is again going back to experiment and see what the theory is predicting, and are you getting that if you perform the experiment at some other time. The more times you get the predictions of the theory correct, it's matching with the experiment, the more confidence we will gain in the theory. But again, it's always temporary and always approximate. Okay, so that's what I had to say. In science, no truth is absolute, and everything has to be measured in experiments. And that is why the first chapter is on units and measurements. Anything that cannot be measured, you cannot say anything scientific about that. For example, I can take the example of souls. Many religions postulate that we have souls which make us alive, right? And in many religions, the idea is that souls are immaterial, that they cannot be detected in any physical experiment. They lie beyond the realm of detection. It may be true, it may be false. Science cannot say anything about that because soul cannot be measured by that very idea of soul. So it lies outside the purview of science. But anyway, so this is how things start, and after this we are going to come to that issue where we always deal with approximate values. You measure these quantities, you got some numbers along with units, which you see here abstractly I have written. They are approximate. That means your device has its own limits. So it's giving you some values. What do you do with those values? Those values are not exact values. Now if you use those values in your calculation to set up relations like this, obviously they will also be approximate. Now how to reduce error? What should this, in your numerical part of that measurement, unit is there, okay. In the numerical part of the measurement, say like that weight, 1.58. If I get 1.584, I have a tendency to not write 4. Will that cause any problem? What are the significant digits? So these are some of the other things that we are going to discuss next. But anyway, that will be all for tonight, or should I say day, because we are uploading during daytime. Tomorrow also we have, of course, every day we have uploads. What do we have tomorrow? Linear algebra. Okay, so see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.